Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hello students, as you know we have started a new topic colloids. And what are colloids? The definitions we have already seen. Colloids are also called colloidal dispersions which exhibit properties intermediate between those of suspensions and solutions. And what are the solutions and suspensions? These kind of definitions we have seen earlier as well. But also while explaining these things I have explained the certain properties of solutions and suspensions you can also see here. And the particles in the colloid are larger than the most simple molecules, and the usually solution contains the solution. The solute molecules are usually molecules, simple molecules or ions. However, in the colloids, the particles are larger than simple molecules. However, they are small enough to not settle out upon standing. So, these particle size in colloids are between are intermediate of the particle size that we see for the solution and the suspension. If you see this picture, you can see this is a solution and the particle size, these are simply molecules or ions. These are particles of the solute, and the particles of the solutes are, you can see they are homogeneously distributed. So the distance and all this kind of distribution, you can see it is a homogeneous. So this is a solution. If you see the on the right side this picture, these are the suspensions. The particle size are very large and they are heterogeneously distributed. So suspensions are heterogeneous mixture. Solution are, solutions are homogeneous mixture. This is a colloid. This is a representative example. The real life example is the milk, and here it is just we see the solution. It is a salt water. Here solution. And this is a mud, the example of the suspension. So the particle size in the colloids, you can see its size is between those of solutes and the suspension. This particle size in the colloids are smaller than the particle size in the suspension and the larger than the particle size that we see in the case of solution. And these particles are also heterogeneously distributed. So suspensions are also heterogeneous mixtures. And these few things we have seen. And what we have also seen that the colloidal particles have an enormous surface area per unit mass due to their small size. And this information people have exploited in heterogeneous catalysis. So the colloidal particles people you have used to made the heterogeneous catalyst in the form of the colloidal particles in that size range, and so they have enhanced the catalytic activity of the heterogeneous catalysts. So this enormous surface area has certain use in the catalysis and this kind of information. So now if you look at the colloid, the particle size in the colloidal range of the colloidal solutions, we see it is between 1 nanometer to 1000 nanometer. So if the particle size is less than 1 nanometer, it will go into the solution, will form true solution. And if the particle size is more than 1000 nanometer, it will form a suspension. So the colloidal solutions usually have the particle size between 1 to 1000 nanometer. Now we also see that the particulate component typically present in a relatively minor amount in the colloidal solutions are called dispersed phase, and the substances of the solutions throughout which that particulate is dispersed is called the dispersion medium. So this is analogous to the dispersed phase is analogous to the solute in the case of solution. So what you see that in the colloidal solutions the solute is dispersed phase, and in the colloidal solutions the solvents are called dispersion medium. So this dispersed phase is dispersed in dispersion medium. So dispersion medium has dispersed phase. Dispersed means distributed, it's separated out. Yeah. And then we saw the classification of colloids. We have seen three different criteria for the classification of colloids. The first is the physical state of dispersed phase and dispersion medium. But we have seen the dispersed phase, there are three states as we know, solid, liquid and gas. So dispersed phase can also be a solid, liquid or gas, and dispersion medium can also be a solid, liquid or gas. So if you make all the combinations, it will be 3 into 3, 9 combinations you can obtain. However, we get only 8 different types of colloids. based on the physical state of dispersed phase and dispersion medium, because gas into gas form always form a homogeneous mixtures, it do not form a colloidal mixture. And so we get only the eight different types of colloidal solutions based on the physical states of dispersed phase and dispersion medium by making all different combinations. These things we have already seen in our previous class. Then another type of criteria is the nature of interaction between dispersed phase and dispersion medium. And based on this, we have seen two different types of colloids, lyophilic and lyophobic colloids. And the third criteria is type of particles of dispersed phase and dispersion medium. Based on this, we have seen three different types of colloids. We'll see just briefly all these things. So let's see the classification of colloids based on the physical state of dispersed phase and dispersion medium. Just the eight different type of colloidal systems are possible, and these eight different type of colloidal systems you can see here. The gas in liquid, the dispersed phase is gas, and gas and dispersion medium is liquid. It forms foam, and the examples are here. Then another is the aerosol. Aerosol is that these are important to the one that are given in the bold. The aerosol, if the dispersed phase is liquid and dispersion medium is gas, it forms aerosol. It forms a colloid, and it's called as aerosol. And if the dispersed phase and dispersion medium both are in the liquid phase, then it forms and when it forms the colloidal solution, it forms, we call it as a emulsion. And the liquid in solid is called gel, and a solid in liquid is called sol. So dispersed phase solid, dispersion medium liquid is sol, and dispersed phase liquid and dispersion medium solid is called gel. And then the classification based of colloids based on the nature of interaction between dispersed phase and dispersion medium. As I have said, we have two different types of colloids, lyophilic and lyophobic. Lyo means solvent or the liquid. So the lyophilic means we know attracting. So it's these colloids are what? Solvent attracting colloids. And solvent attracting colloids means the dispersed phase is attracted to the solvent or the liquid that is there, means to the dispersion medium. So there is a natural attraction between dispersed phase and the dispersion medium. However, the lyophobic solenoids, they do not have a natural attraction between the dispersed phase and the dispersion medium. These are called lyophobic. Lyo means we know the solvent, and phobic means repellent. And so lyophilic colloids are also called the reversible salts or the reversible colloids. Why they are called salts? Because usually, as we know the definition here, the salts, the solid and liquid, dispersed phase solid, dispersion medium liquid, and we are talking here about the solvent attracting and the solvent repelling. It means the dispersion medium is liquid here, and the dispersed phase in that case is the solid is in the solid state, or is a solid, so they are also called salts. So the lyophilic salts and the lyophilic salts, these are reversible salts. Reversible means if by any method you remove the dispersion medium, it will, what will be left over is only the dispersed phase, and next, soon as you add the dispersion medium, it will again form the colloidal solution or the colloid, and so this is called a reversible salt. So reversible salt means it can be reversed. It can be, the solvent can be dried upon, or the dispersion medium can be dried upon, or the evaporated, and then after the evaporation of the dispersion medium, you add the dispersion medium, you can get back the colloidal source, or you can get back the colloidal source or colloids, and this is called the reversible source or reversible colloids. And these salts are very stable and do not get easily coagulated. The lyophobic salts, usually it means that we know the liquid heating, and these lyophobic salts are not very stable salts. We need certain stabilizing agents for their preservations, and they are irreversible salts as well. Means once by any method you remove the dispersion medium, to make these salts you again need a special method to prepare the colloid. So lyophobic colloids, usually we need a special method to form such colloids, because there is no natural attraction between these things. And these things, other things we have already seen. The classification of colloids based on the types of particles of dispersed phase and dispersion medium. As I said, based on this, there are three different types of colloids. One is called the multimolecular colloids. Multimolecular, once you understand the meaning of multimolecular, multi means many, and molecular means molecules. If the many molecules get aggregated, get together to form the colloidal particles, then this is called multimolecular colloids. And so it means it may be that a larger particle or the precipitate is broken down into a smaller pieces, which and each of these pieces in the colloidal range, colloidal size range, and each of these pieces contains many molecules, multiple molecules, then such colloids are called multimolecular colloids, where the particle size must be between 1 to 10 nanometer, then only it will form the colloidal solution. And the macromolecular, the examples that you can see, the gold salts or the sulfur salts are example of multimolecular salts. The macromolecular salts. Again, the definition is already there in this term. So macro means the large, and the molecular, so one large molecule itself, if it is in the size of the colloidal particles, then it will form the macromolecular colloids. And what kind of molecules will have such a large size? Definitely, it will be a polymer. This polymer can be a biological polymer or can be a synthetic polymer. Biological polymers, we know what are the biological polymers. This can be starch, cellulose, proteins, enzymes, gelatins, or the synthetic polymers could be nylon, polythene, plastic, polystyrene, etc. Let us now see the associated colloids, and from associated colloids, I link to what we are going to study, what I have planned to teach you in the today's class. So, associated colloids. Here, the associated colloids means the particles and molecules are already there, so the ions are there. These ions behave differently at lower and higher concentrations. If they are at the lower concentration, what will they will these all the ions will be separated, all the molecules will be in the separated will be separated. They will be in the they will exist as the individual ions. But once they are there in a certain concentration, they will now start aggregating. They will start getting associated, and so they will form the associated colloids. And usually, we know the surface active reagents like the soaps and detergents form this kind of associated colloids, and these are also called associated colloids, are also called micelles, as you can see here. So certain substances on dilution in a medium behave as a normal electrolyte at low concentrations, but behave as a colloidal particles at higher concentrations due to formation of aggregate. Normal electrolytes means it will electrolytes usually get dissociated into water, and so the ions will be separated out. But at the higher concentrations, they'll these all the ions they'll start getting associated, and because the association, they will form the particles of the colloidal range, and so such colloids are called associated colloids, and the aggregated particles are called micelles. So all the aggregated particles or the associated particles are called micelles. The formation of micelles take place only above a particular temperature, and this temperature is called a Kraft temperature. So below this temperature, the association of these particles will not take place, so the micelle will not form, and this temperature is called the Kraft temperature. So this is the threshold temperature above which the micelle formation take place, and that this micelle formation also depends on the concentration. As I said, the above a particular concentration, a threshold concentration, only the micelle formation starts, and that concentration is called critical micelle concentration, and CMC in short. CMC, critical micelle concentration. So the formation of micelle take place above a particular concentration, which is called a critical micelle concentration. Which is called critical micelle concentration, thus or CMC. So these micelles may contain as many as 100 molecules or more. These colloids have both lyophobic and lyophilic parts, and if they have any molecule is having both lyophobic and lyophilic part in it, such molecules or particles are called amphiphilic particles or amphiphilic molecules. So the term comes is the amphiphilic, M-P-A-M-P-H-I, philic spelling we already know, P-H-I-L-I-C, amphiphilic means it has both the parts, lyophobic parts and lyophilic parts. Or if the solution, if the solvent is water, so you can call it as hydrophobic or hydrophilic. So hydrophobic, hydrophilic. Lyo means solvent or any other liquid. So then the general term is lyophobic or lyophilic. These colloids, the associative colloids, revert to individual particles on dilution, which are usually ions. And these things I have explained earlier. The minimum concentration required for micelle formation depends upon the nature of the dispersed phase, and definitely it should depend. Different dispersed phase have different properties, and different dispersed phase means different type of molecules which form this dispersed phase, or the substances which form this dispersed phase, and all those substances have different associative properties, different associative tendencies. So definitely this CMC, the critical micelle concentration, will depend on those dispersed phase or the substances which forms the dispersed phase. The associated colloids are usually formed by surfactants, or the surfactants are also called surface active agents, unlike soaps and synthetic detergents. The surfactants means anything which reduces the surface area are called usually surfactants. These agents form micelles when present in solution at concentration greater than CMC. So the CMC what? So the soaps and synthetic detergents, they form micelles when present in solution at a concentration greater than CMC. The critical micelle concentration and the critical micelle concentration may vary soap to soap or detergent to detergent. For general soaps, the CMC is 10 to the power minus 4 to 10 to the power minus 3. It's a range. And for soaps, if the CMC is in this range, mole per liter means the molar concentration. So you can see it's not a fixed concentration, it's between this concentration. For soaps, the CMC value is critical micelle concentration is this 10 to the power minus 4 to 10 to the power minus 3 molar. Let us first now see the soaps and detergents, and after the soaps and detergents, I'll show you how the mechanism of or explain you the mechanism of micelle formation, and after that I'll also show the how the cleansing action of the soaps or detergents. It means how the soaps and detergents works when we use, how they clean the clothes and so. The soaps and detergents. The pioneers made soaps by boiling fat with strongly basic solutions made by leaching potassium carbonate K2, which is K2CO3 from wood ashes with hot water. So wood ashes contains K2CO3. So K2CO3 is already there in wood ashes. If you just pass hot water, this K2CO3 will get dissolved in the hot water, and then you can take out this hot water and you add this hot water to a boiling fat, it will form the soap. So this is how people were making this. Earlier people made this the first time. This is how the soaps were made. The pioneers means that in the beginning. So animal fat contains what is the fat? As I'm saying, the boiling fat. So what is the fat? So animal fat is the fat is one of the example of the fat contains polyesters of fatty acids. And the fatty acids are what? The long chain carboxylic acids. Carboxylic acids, you know what are the carboxylic acid? An alkyl group is there, and which is attached to the C double bond O group, and then C double bond group on other side is attached to OH group. If the carbonyl group C double O is linked to one alkyl chain on the one side and the OH group on the other side, such molecules are called carboxylic acids. These are organic molecules, and these are organic acids. So fatty acids are such organic acids, but the alkyl chain, the R group is longer. In this case, if the R group is very long, then we call such groups are carboxylic acids as a fatty acid. The example you can see here. This is a very long hydrocarbon chain, the alkyl group, and if this is up to here, if this to add H here and remove this part, so this will be one fatty acid. This will be another fatty acid, the part of another fatty acid. Only H group is not here. This is another fatty acid. These are all the fatty acids. And these are polyesters. Now, esters we know another functional group. In the esters, in the O group is attached to one alkyl group, and as you can see here, this is ester. This oxygen is attached to another carbon atom, and on this side also the alkyl group is there. This is also an ester. This is also an ester. In reality, this is an ester of polyester. It is three esters are here. This is polyester. This molecule up to here. If this is OH, this is also OH. This is also OH. This is glycerol. So glycerol when reacts with when combines with the fatty acids and all the OH group make the ester bond, then we call such molecules or such chemical substances as a fat. So this is an example of a fat. So when animal fats are treated with a base like potassium carbonate or sodium hydroxide, these are the bases, glycerol and salts of fatty acids. And examples of the fatty acids are oleic acid, palmitic acid, stearic acids, and the salts of these fatty acids are formed. So that you can name them. That this fatty acid will have one name, this will have another name, this will have another name. You don't have to remember all those names. It's not in your syllabus and not in your requirement. But certain examples you should know: oleic acid, palmitic acid, stearic acid. These are the fatty acids. What are their structure and other things? It may not be required to. So the when this we add base to this molecule or this substance, what happens? These fats they get hydrolyzed, and on the hydrolysis, what will happen? This group, this bond will be broken, this ester bond will be broken, this will be broken, this will be broken, and if the ester bond is broken, we see here the formation of OH group, and this OH group will not be because we have added base, so this OH group is the proton will be not there because OH group is there means it is a carboxylic acid. So actually it forms a salt in the presence of base. So it will be the salt of this fatty acid, salt of this fatty acid, salt of this fatty acid, and this O group it will get this is OH, this alcohol. So alcohol's acidity is not very high; it's less than that water, and so we can see it will form OH group, OH group, OH group, and so it is a glycerol. So when the animal fats are treated with the base, it forms glycerol and then the salts of sodium or potassium salts of fatty acids. The sodium or potassium salts of fatty acids are called soaps. And so these salts are actually called soaps. Sodium or potassium salts of fatty acids. And this fatty acid contains an alkyl group and a carboxylate ion at the end. And the carboxylate ion, and to balance the charge of the carboxylate ion, anyway, potassium or sodium ion will be there, and so it will form a salt. The soaps are represented by RCOO minus Na. This R is a long hydrocarbon chain, and the example of the soaps are sodium stearate, which is a major component of many bar soaps, and the sodium stearate it contains an alkyl chain and having 17 carbon atoms, and so that the terminal it will be CH3 and then CH2 16. So this CH2 16 and COO minus is series carbon. This is not part of the alkyl chain. This is a part of the functional group, that a carboxylate group, and this Na plus COO minus Na plus. This is a salt. And the structure of this one can write in this way. This is CH3, CH2, all these 16 CH2 groups, and the COO minus Na. This one. And this, as you can see, this is ion, this is ion, this is called ionic end, and this is the hydrocarbon chain end. These are the hydrocarbon chain end, and this is ionic end. These ions are there. So in aqueous solution, if you add the salts of sodium or potassium salts of fatty acids. So these are salts which are called soaps. If you add soaps in water, what will happen? These salts, these ions will get separated. Usually it happens if the ions are dissolved or the ionic compound is dissolved in water, the ions will get separated. So these are here this gets easily separated out. So the when dissolved in water, it dissociates. This group dissociates into RC double minus and Na plus ions. The length of this hydrocarbon end can vary from soap to soap. Different soap this hydrocarbon and this is for the stearate or the stearic acid. If this was a COOH, can call it a stearic acid, which is a fatty acid. And so this hydrocarbon chain end can vary fatty acid to fatty acid, and based on this hydrocarbon chain, one can form a different fatty acid, obtain a different fatty acid. Anyway, these things are very understandable. Now, this on the dissolving in water, this salts of sodium or potassium salt of fatty acid will dissociate into RCOO minus ion and Na plus ion. So RCOO minus ion, this and Na plus ion. So one can obtain here this RCOO minus ion. And this is the hydrocarbon part which is called the hydrocarbon end or the tail, or this is also actually the hydrophobic because it is non-polar, and this is a non-polar, so it is hydrophobic, and this is polar, and so it is hydrophilic. It interacts with water. It has affinity, strong affinity with water, but this one doesn't like water because it is non-polar. So this is hydrophobic, hydrophilic head. This is called hydrophilic, and it is called head, and this one is called tail of this ion. So this is hydrophobic tail, and this is stearate ion. Actually, in all, it is an stearate ion. The RCOO minus ion consists of two parts, a long hydrocarbon chain R, also called non-polar tail, which is hydrophobic, means a water repelling, and a polar group COO minus, also called polar ionic head, which is hydrophilic or the water loving. Molecules such as these are termed amphiphilic. As I said earlier, the molecules like this are called amphiphilic. This is an amphiphilic ion. This is hydrophilic and this portion, and this is hydrophobic portion, and both are there in the same ion. So this is called amphiphilic ion. Or if it was an acid, this OH, so fatty acids are amphiphilic molecules. Or so now one can represent these ions, the amphiphilic ion or the stearate ion, as this, the hydrophobic tail, and this is the hydrophilic head. So this is head and this is tail. This is a general representation of a soap or a fatty acid. People also represent a fatty acid in this form because even in the fatty acid, COOH is the hydrophilic part. So in water, the RCOO minus ions are present on the surface with their COO minus groups in water, and the hydrocarbon chain are staying away from it and remains at the surface. So if they are at the very low concentration, and what happens is RCOO minus ion. COO minus ion has a great affinity with water, so it will be dipped in water. And R group doesn't interact like to interact with water. It is hydrophobic, so it will be away, it will stay away from the water, and so these molecules at the lower concentration will always be at the surface so that the hydrophobic tail can stay away from the water, and the hydrophilic tail will be submerged into the water. I means the head group, hydrophilic part, COO minus, will be submerged into water, or it will be dipped into the water. And the detergents or the which soap substitutes, which are soap substitutes, also contains non-polar hydrocarbon chains. So these things we will see. So the detergents are also contains non-polar hydrocarbon chains such as C12H25, and this is a part of sodium lauryl, so sulfate, and an ionic group such as sulfate, this SO3 minus, or sulfonate SO3 minus. Sulfate ion, you know, SO4 double minus, but this is a sulfate group, and actually one minus ion is less here because this oxygen atom is covalently linked to a carbon atom, and so this is O, and only one oxygen atom is having a negative, means only one negative charge is here, and so this is sulfate group. And the sulfonate group, the sulfur is linked to a carbon atom of the alkyl group. So the sulfur is linked to the carbon atom. So this is sulfonate. So detergents have the long chain hydrocarbon or the non-polar hydrocarbon chain, as well as the hydrophilic part in the form of sulfate or sulfonate. The example of the detergent is the sodium lauryl sulfate, which is detergent, and this sodium lauryl sulfate, this is sulfate, and this is a part of, if this was not here, this is called, we can call it as a sodium lauryl sulfate, and this is sodium. So this is sodium, and this is lauryl sulfate, you can say. So sodium lauric acid, you can, when react with the base, will form the sodium lauryl sulfate. The length of the hydrocarbon end can vary from detergent to detergent, as we have seen in the case of soaps. The length of hydrocarbon chain can vary soap to soap. So here in the case of detergents also, the length of alkyl chain may vary detergent to detergent. So this is the hydrophobic part, and this is the hydrophilic part. So it can also have a head part and the tail part. Head, hydrophilic head, and hydrophobic hydrophobic tail, and this is also an amphiphilic ion or the amphiphilic molecule, one can say. The length of like soaps, the polar sulfate or sulfonate groups, being hydrophilic, as I said, interact with water, and the alkyl groups stay away from it in a detergent water mixture. So in a detergent water mixture like soap water mixture, what happens? The hydrophilic group will interact with water, it will submerge, or into the water and the hydrophobic group stay away. So the detergents also stays at the lower concentration only on the surface of water. Soaps form insoluble calcium and magnesium compounds in hard water. These things we have already seen in the hydrogen chapter. And on the other hand, the detergents form water soluble products, which is a definite advantage for detergents. So detergents do not form any insoluble calcium or magnesium compounds or the coordination compounds of the calcium or magnesium. Soaps forms, detergents do not form. And now let's see the mechanism of micelle formation. So as I said, if the soap or detergent is there, the hydrophilic part will be submerged into the water or dipped into water at the lower concentration, and the hydrophobic part will stay away from the water. So you can see here in this case, in this figure, this is a hydrophobic tail which is staying away from the water, and the hydrophilic head is dipped into the water. So this is stearate ion, and this is water, and this is the hydrocarbon part. So as soaps are amphiphilic molecules, on mixing with water in lower concentrations, their hydrophilic head turns towards the water and interacts with it, and the parts, hydrophilic tail part stays away. So hydrophobic tail part is staying away. You can see here the soaps mostly stay at the surface of water at low concentration. At critical micelle concentrations, the anions of the soaps are pulled into the bulk of solution and aggregate to form a spherical shape with their hydrocarbon tails pointing towards the center of the sphere with COO minus part remaining outwards on the surface of the sphere. So what happens at a higher concentration or at a critical concentration or micelle concentration or above it, what happens? These soap molecules will be pulled into the water. These ions of the soap will be pulled into the water. And why these ions? The cations will anyway be dissociated from this part, and the cations will be there and will go into the solution of the water. And so it will be pulled into the water, and it will pulled in such a way that this hydrophobic part will form the core, and so hydrophobic parts will be centralized or it will be buried, and the COO minus parts will stay away. It will be staying on the surface and it will form a spherical shape, mm, structure. And this spherical shape, spherical structure is called micelle, or this, since this is micelle of ions, so one can also call it as an ionic micelle. And so this COO minus part stays away and it will interact with water. And another thing is C double, this is also having negative charge. This is also is having negative charge. So if this is at the surface, here the area will be more, so that there is a repulsion. So they will not like to be very closer together. However, the hydrophobic tails, this hydrophobic part, these parts they can interact with each other through the dispersion process. And because of the dispersion forces may also work between these ends, but the stronger electrostatic repulsion will be more dominant over the dispersion interactions or dispersion attractions. However, in the case of hydrophobic tails, there is no repulsion between them. Only the dispersion forces will work, and they are long tails, so it will be energetically favorable as well. So the an aggregate thus formed is known as ionic micelles. So these are ionic micelles. These micelles may contain as many as 100 such ions. In the case of detergents, example sodium lauryl sulfate, the example we have seen earlier, the polar group is SO4 minus, the sulfate group, along with the long hydrocarbon chain. Hence, the mechanism of micelle formation is also the same as that of the soaps. So, the micelle formation, the mechanism is we see for the detergent is also same as that of the soaps. The COO minus groups of the soaps of different COO minus groups of different RCO minus ions tend to stay away from one another due to the like charges, where the R groups try to approach each other to form a bunch. As I said, they try to approach each other, and this approach means they'll interact with each other to dispersion process, and this leads to the formation of a micelle. And also, once they are buried inside, they will be staying away from the water. So the hydrophobic, they are hydrophobic part, but they can have a natural interaction between them, and there is a dispersion interaction. But they do not like water, so they are anyway in this micelle form. They are in the core of this sphere, so they are anyway staying away from the water. Thus, a soap or detergent micelle is a negatively charged colloid particles in which the negatively charged C double O minus groups are arranged in a spherical manner at the surface. At the same time, the hydrocarbon chain points toward the center. These things we have already seen. Let's now see the cleansing action of soaps. As we know, as you know, till that the micelle consists of a hydrophobic hydrocarbon like central core. This is the central core is the hydrophobic hydrocarbon. It contains this micelles. This thing we know. The cleansing action of soap is because soap molecules form micelle around the oil droplets. So suppose an iron droplet is on a cloth. So what will happen? The ions of the soap will form micelle around this oil droplet. So the and the oil droplet and the hydrophobic part of this stearate ion, you can say is the example, or any ion, the fatty acid ion goes into the oil droplet. The hydrophobic part will go into the oil droplet because oils are anyway they are organic molecules. So the grease, they are organic molecules, and this hydrophobic part will have a stronger interaction with them. It can interact with that. So it will go inside the oil droplet, and the hydrophilic part projects out of the grease droplets like the bristles, and the hydrophilic part will be out of it and it will be interacting with water. Since and once you will shake this water, what will come? So since the polar groups can interact with water, the oil droplet surrounded by a stearate ion is now pulled into water and removed from the dirty surface. Thus, soap helps in emulsification and washing away of oils and fats. Let's try to understand this mechanism in this figure. So the negatively charged sheath around the globules prevents them from coming together and forming aggregates. So let's see, suppose this is a surface and this is a grease is on the surface, and this you have just used a soap or detergent dissolved in water. So this is a mixture of soap and detergent with water. So what will happen after some time, this hydrophobic parts of this will, if at a lower concentration, it will be initially on the surface, but at a certain concentration, the critical micelle concentration and above it, it will start coming into the solution. Once it will start coming into the solution, it will like go to the grease, and this hydrophobic part will go inside the grease, and other oil, this will go inside the grease, and the hydrophilic part will stay away and will be interacting with water. And anyway, with that, you will also be shaking it, and not only by shaking, what will happen, the interaction of these interactions are energetically favorable. So the system will try to maximize these kind of interactions. And so that this oil or grease will now will be it will start getting removed from the surface, so that such interaction can be maximized. And also because you are shaking, so with the water current, this is also being shaked because it will be interacting with water, and so this will get removed from the surface. And once it will go out, even the slight part, if it is coming out of the surface as new molecules of this ion, the amphiphilic ion will come and start interacting with this, because this portion is now has now come in contact with this solution. And so this way, finally what happens, the micelle formation will be happening, and with this micelle formation, this hydrophilic group, as soon as you wash out this solution, this will get out from the close of the surface. So agitation begins to the surfactant ions oriented themselves in grease and water. As you can see here, agitation begins to separate grease from the surface, and the process continues. The cleansing complete. Now you can see the clean surface. This is being removed from here, from the surface. Let us now see the preparation of colloids and how the colloids are prepared. Let us first see the preparation of lyophilic colloids. The lyophilic colloids, the definition we have already seen. Lyophilic means liquid loving colloids. On the liquid loving colloids, the colloidal particles have great interactions with the liquid. It will like to interact with the liquid or the dispersion medium. The lyophilic colloids have a strong affinity between particles of the dispersed phase and dispersion medium. Since this is a more technical term, the dispersed phase and dispersion medium will have a great affinity. Simply mixing the dispersed phase and dispersion medium under ordinary conditions readily forms this colloidal solution. So just by mixing the dispersed phase and dispersion medium can form this lyophilic colloids. For example, substances like gelatin, gum, starch, egg albumin, etc. pass readily into water to give a colloidal solution. So you don't need any special method to prepare lyophilic colloids. These are reversible in nature, we have seen, because they can be precipitated and directly converted into a colloidal state again. So these are reversible in nature. Let us now see how one can prepare the lyophobic colloids. And as I said earlier, the lyophobic colloids need special methods to be prepared. So lyophobic, and as they are also not very stable colloids, and the stable colloids only adding a small amount of electrolyte or other things may start making the precipitates. So we need certain stabilizing agents to make this lyophobic colloids stable. These things we have seen earlier. Anyway, lyophobic colloids can be prepared by mainly two methods. And one method is called condensation method and another is dispersion method. Again, if you know this, the meaning of this word, this condensation and dispersion, you can easily understand the difference between these methods. Condensation method, you know the condensation of the water droplets to form water droplets condense to form clouds. Similarly, means the water, the small particles, or maybe in the case of colloidal solution, atoms may get aggregated or the ions get aggregated to form the colloidal particles. So the this aggregation one can call as a condensation. And the dispersion method. Dispersion method means you start with a solid substance and it is dispersed, it is broken, maybe it is broken into the atoms and then atoms get associated, or maybe it is broken into the smaller particles which is in the colloidal size. So this is the dispersion. Dispersion, you know, dispersion is distribution, the broken. So this is dispersion or the separation. So these two methods are there. The more common method, the condensation methods and dispersion method. The condensation means the smaller particles of dispersed phase are condensed to colloidal size. So condensation method, as I said, a smaller particles of the dispersed phase are condensed to colloidal size. And there are certain methods that by which we can make the colloids using the condensation methods, and the different colloidal particles require different attention, different methods to be prepared. So some colloid particles are made of colloidal solution are made by oxidation. So a colloidal solution of sulfur can be obtained by bubbling oxygen or any other oxidizing agent like HM3 or bromine or any other thing, etc. to a solution of hydrogen sulfide in water. So hydrogen sulfide solution in water is already there. You add one oxidizing agent, which could be oxygen or any other thing, HNO3, Br2, SO2, SO. So the on oxidation, what happens? The water molecules will be formed, and also the sulfur, these atoms will be reduced. So H2S is here in the this minus two oxidation state, and it is now in the atomic form. So the oxidation state is zero. Now the sulfur atoms will aggregate. Initially will combine to form S8 molecule, and the S8 molecules will then aggregate to form the colloidal size particles. So this method you can see is the condensation method, because the atoms are formed because of this chemical reaction, the oxidation reaction, and these atoms aggregate to form the sulfur salt. The sulfur atoms aggregate to form form sulfur salt. Similarly, this H2S, another oxidizing agent, could be SO2, and the oxidation method it also forms the sulfur salt, and the water molecules will be formed as a side product. Now another method is by reduction. Certain molecules or certain salts are prepared by the reduction method. Oxidation method may not work in them in their case. The reduction, so many metals such as silver, gold, platinum, etc. have been obtained in the colloidal state by treating the aqueous solution of their salts with a suitable reducing agents such as formaldehyde, phenylhydrazine, hydrogen peroxide, stannous chloride, etc. That's some examples like that. For the gold salt, the example is here. So gold salt, this salt of the gold is there, and there AuCl3. gold 3 chloride, and then this reducing agent is SnCl2. Once you add the reducing agent SnCl2, then anyway the reduction will happen, reduction of this AU, the gold will happen. So AU from plus 3 oxidation state will be converted into the AU atom, the gold atoms, and these gold atoms will aggregate to form the colloidal size particles, so the gold sol will be obtained. The AuCl3 we can also use another oxidizing agent like this is formaldehyde in water, and then the reduction we again get the gold salt, and these other products will be formed. Now by hydrolysis also some kind of salts or some kinds of colloids are formed by the hydrolysis, and these are all under the condensation methods. As you can see, the smaller particles or the atoms are formed, and which aggregates to form the colloidal size particles, the atoms or maybe molecules. So the many salt solutions are rapidly hydrolyzed by boiling dilute solutions of their salts. For example, ferric hydroxides and aluminum hydroxide salts are obtained by boiling solutions of the corresponding chlorides. And so it means ApCl3, and if you use the dilute solution of ApCl3 and hydrolyze it, what will happen? ApOH thrice the iron 3 hydroxide will be formed. This is we can also called ferric hydroxide. Ferric hydroxide is not dissolved in water, so you can call it as a molecule. And this molecule on aggregation will form the ApOH3 salts or the colloidal solution. Now, this is one method. So by double decomposition. The double decomposition, a salt of arsenic sulfide is obtained by passing hydrogen sulfide through a cold solution of arsenic oxide in water. And the, this AS2O3 arsenic oxide, when it reacts with H2S gas, a double decomposition reaction happens and it will form arsenic sulfide. This arsenic sulfide and three water molecules. This arsenic sulfides will now aggregate, get many arsenic sulfides will get associated, they will get aggregated, they get condensed to form a AS2S3 salt or the arsenic sulfide salts or arsenic sulfide colloid. So by exchange, and why this is double decomposition, you can see this is also decomposed, means the broken. Here it is only the exchange of the anion between two cations. The sulfur has gone with the arsenic, this cation, and oxygen has gone to the hydrogen. So it is a cation in this case. One can, although this is a molecule, but it will have partial positive charge, so one can treat it as a cation. I'm just telling this, not in the real technical term, you cannot call it as H plus ion and H minus, H double minus ion, but for an understanding, you can just consider this H plus, since it is its oxidation state is plus one, and sorry, the sulfide is in minus two oxidation state. So one can consider this as and assume this as an anion and this is a cation, and you can see that the both molecules are decomposed and their corresponding ions are exchanged. So these things form. This sol is formed. So these molecules are formed, these molecules get condensed, many molecules get together to form this sol. So by exchange of solvent. So certain colloids are formed by the exchange of solvents. The colloidal solutions of certain substances such as sulfur, phosphorus, which are soluble in alcohol but insoluble in water, can be prepared by pouring their alcoholic solution in excess of water. So these solutions, sulfur and phosphorus, are dissolved in alcohol. Once so that they are dissolved in alcohol, so all the atoms are separated out. Means the molecules of the sulfur and phosphorus are separated out. Maybe P4 molecules, A8 molecules will be separated out in the alcohol, and that is why they are dissolved in alcohol. Once you put this solution into the water, and because they are not dissolved, they are not soluble in water, so they will get associated. They will start getting associated to, so which is a condensation process, and after association they will form the colloidal size particles. So for example, alcoholic solution of sulfur pouring into water gives a milky colloidal solution of sulfur. This is a colloidal solution of sulfur and milky in color. Another method is the changing the physical state. So one can also obtain the colloidal solution by changing the physical state of certain colloids of salts of substances like mercury and sulfur are prepared by passing their vapors through cold water containing a suitable stabilizer such as ammonium salt or citrate. So what happens? So by exchanging, so what is the vapor of mercury or sulfur mercury in liquid state sulfur solid. So you can use their vapors, and these vapors, when it is passed through the cold, the vapors, the physical state is the gaseous state. When it is passed through the cold water containing a suitable stabilizer, so these particles, the vapors in the vapor form, they will be separated. All the molecules or the atoms are separated out, individual molecules. They will now get condensed. They will get together to form colloidal size particles, and the stabilizer that may be used here is the ammonium salt or citrate. Now let us now see the dispersion method. Dispersion method means what? The larger particles of a substance or suspension are broken into smaller particles. And the following methods are employed here. So there could be the by electrical dispersion or Brake's arc method. So electrical dispersion or Brake's arc method are dispersion method, and dispersion method is where larger particles are broken into smaller particles, and so these smaller particles will be in the size of the colloid, or maybe that these smaller particles, maybe even the atoms, and these atoms will then get associated to form the colloidal particles. So the electrical dispersion or Briggs arc method, let's now see what is this. So this method is used to prepare platinum, silver, copper or gold salts, and this is the method what let's see here. This is a metal electrode, and the metal electrode means these are the metals. You can just see the examples: platinum, silver, copper or gold, and these are the metals of which you want to form the colloidal solution. So the metal whose salt is to be prepared is made as two electrodes which is immersed in a dispersion medium such as water. So these metals whose salts has to be prepared, they will be submerged into or immersed into the dispersion medium, which could be water. And as you can see here, this is a metal rod. It is immersed into this, and this is a dispersion medium, which is water. And between these two electrodes, what we have added here is the electrical arc, which is just suspended between them. And this electrical arc will actually produce heat, and because of this production of very high heat, these metals will get vaporized. And these metals, the atoms will get vaporized. It means this rod will get all the atoms will be separated out in the form of atoms, and these atoms then will get associated because here we have added the ice, and they will get condensed to form the colloidal size particles. So the dispersion medium is kept cool by ice. So ice is, you can see here, an electrical arc is struck between the electrodes. The electrical arc is a metal electrode. uh, Tremendous heat produced vaporizes the metal, which then condenses to form particles of colloidal size. Thus, this process involves dispersion as well as condensation. So, initially it is dispersion. So, from the solid rod, the atoms will be definite, separated atoms will be dispersed. Now, these atoms will be condensed to form the colloidal size particles. So, one can say this is dispersion cum condensation method, or this, and this is kept actually in the dispersion. So, the colloidal solution prepared is stabilized by adding a small amount of potassium hydroxide to it. Now let's see this peptidation method. The peptidation method also comes under the dispersion method. The converting a freshly prepared, what is peptidation? The converting a freshly prepared precipitate into a colloidal form by adding a suitable electrolyte is called peptidation. So during a chemical reaction, once the precipitate is formed, this is just the freshly prepared precipitate. Now by adding certain reagents, chemical reagents, which could be electrolyte, if you make the colloidal size particles, this process is called peptidation. The cause of peptidation is the adsorption of ions of the electrolyte by particles of the precipitate. This method is applied generally to convert a freshly prepared precipitate into a colloidal salt. The electrolyte used for this purpose is called peptizing agent or stabilizing agent. So anyway, the peptidation what helps is electrolyte, and so the electrolyte is called peptizing agent because this is stabilizing, this is making the colloid. So This is making the peptidation process happening. So this is they are called electrolytes are called peptiding agent or the stabilizing agent. Important peptiding agents could be electrolytes or maybe the sugar, gum, gelatin as well. Let us see one example of the peptidation. So freshly prepared ferric hydroxide can be converted into a colloidal state by shaking it with water containing Fe3 plus ion or OH minus ion. So the electrolyte which contains Fe3 plus ion could be FeCl3 and the electrolyte containing OH minus ion could be NH4OH. And so let's see this freshly prepared FeOH3 precipitate. This FeOH3 precipitate with addition of FeCl3. The Fe3 plus ions will be there. This will be broken into Fe3 plus ions plus 3 Cl minus ions. Now this Fe3 plus ions will get absorbed on this precipitate and so it forms this separate particles in the colloidal size. You can see here this is a freshly prepared ferric hydroxide precipitate. On addition of FeCl3, it forms a colloidal charge particles, and each particle contains now the positive charge in this case. And because of the formation of positive charge, these colloidal particles will not get clung to each other. And this is thus we form the colloidal sol, and this colloidal sol FeOH thrice and some Fe atom, so it will have all the sols. These particles or the colloidal particles are positively charged in this case. And if you as OH minus ions, OH minus ions get absorbed, so in that case the colloidal salts will contain negative charge on it. So during peptidation, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes the development of positive or negative charge on the precipitate, which ultimately breaks up into a smaller particles because many, if suppose positive charge get absorbed on it, and because of the positive charge repulsion, it will break down. It will broken into a smaller piece of negative charge. They will also be repelling. So the precipitate all over the surface, if such charges are absorbed, so this precipitate will broken into a smaller pieces and smaller particles and of the size which are of the colloidal size, and so we can prepare the colloid by the method which called the peptidation. So dispersion method we have to study only two methods, the Brady's arc method or the electrical dispersion. This is the Brady's arc method and the electrical dispersion method or the peptidation method. The peptidation term and what is the definition of peptiding agent or stabilizing agent you should remember. I'll stop this lecture here. I hope you enjoyed it.